Hi class, I'm about to make the strangest video of all time because my screencast software doesn't work. So hopefully this works for you guys and you can hear everything I'm saying. Today we're talking about evaluating logarithms. So it's kind of a review of what we talked about yesterday. You're going to have something like this where you're going to solve for x, okay? So you're basically undoing exponents to solve a logarithm. So let's recall that a logarithm is just an exponent, okay? And if we have y equals log base a of x, that is the same thing as saying, okay, the base is a, so a to the y equals x. So I always think about it this way. It's a to the y equals x. A to the y equals x. So if you want to actually solve a simple exponential equation, you can either graph both sides and find the point of intersection, or you can express both sides with a common base and then use guess and check, or you can rewrite as a logarithm if you're given an exponential equation. Okay, so I'm going to show you how to use all three methods to solve this. So we have 16,384 equals 4 to the x. So that's quite a large number. So the first method would be to go onto GeoGebra, and if I was on my computer, I would show you this. But you can graph the function y equals 4 to the x. And you can graph the function y equals 16,384. Okay, sorry, 84, not 48. And then you would have to obviously change your scale so you could see the point of intersection. But where they intersect would be the solution. So if you had a sketch of this, it would basically look something like this. So you'd have your exponential function here. And you would have your horizontal line here. This continues that way. And the point of intersection would be here, and you would be able to find that that would be at x equals 7. So that is the solution. So you could use graphing software to do that, or you could even use the CAS, the computer algebra software, and it'll solve that for you very nicely. Okay, step 2 is to basically test x values. So that's what we were doing last year. So how big? 4 to the what equals 16,384. So 4 to the 4, I put that in, I get 256. That's obviously way too low. So I'm going to go quite a bit higher, 4 to the 8. But then that gives me 65,536. That's too high. So I try 4 to the 7, and I get 16,384. So therefore, x equals 7 is the solution. So a little guess and check. Okay, so the third option, which is kind of what we're working towards, is that we want to rewrite this as log base 4, because the exponent base is 4, so our log base will be 4, of 16,384 equals x. And then we want to solve for x. So this is what we want to work towards. So later next week, or later in this week, you will learn to use your calculators to solve that. Okay, but we haven't learned that yet. Okay, but you will soon be learning how to use your calculator to solve something like that. All right, so here we have, so those are x, that's an exponential equation because it's in exponential form. Excuse me. Now we have some logarithmic functions because they are in logarithmic form. So when you're giving this, the best way to do it is to rewrite as an exponent for now until we learn how to use our calculators. So it's going to be this to the this equals this, okay? So it's always base to this equals this. So 4 to the x equals 64. Okay, so you might know right off the bat that x equals 3, or you might need to use your calculator to test, but x equals 3 is the correct answer. Okay, here we have remember this is the base, to this equals 1 over 27. So I always think about this, 3 to the what equals 1 over 27. Well, I know x has to be negative because this is a fraction, and x to the 3 gives me 27, so this must be x equals negative 3. Okay, because for an integer, a whole number to turn into a fraction, it must be negative. Okay, and 3 to the power 3 is 27, so 3 to the negative 3 is 1 over 27. Okay, when you have radicals here, you want to rewrite as a rational exponent. So that means an exponent with fractions. So 5 to the x equals 25 to the 1/3. Okay, so that's how this can be rewritten. Okay, that means that it's to the 3rd root, okay, which is the 1/3 exponent. So how can we do this? Well, it is best to rewrite this with base 5 so we can compare, because this side has base 5, so let's rewrite this with base 5. Okay, so 5 to the x equals 5 squared to the 1/3. Okay, it's important that I put that in brackets. So now the power of a power law says that I have 5 to the power x equals 5 to the 2/3. So since the bases are the same, the exponents have to be the same. So x equals 2/3. Okay. Now we move on to example 3. So solve log 2, base 2 of negative 4 equals x. So this is the same as writing 2 to the x equals negative 4. Now, what power of 2 will give us a negative number? If we put a negative number here, like 2 to the negative 1, that would give us 1/2. And 2 to the negative 2, for instance, would give us 1/4. So that doesn't work. Wah, wah. And if I go to a fraction, 2 to the 1/2 or something like that, that's just the square root of 2. So there's actually no way to get a negative here. Another way of thinking about it is think about the graph of 2 to the x. That just looks like this, right? And negative 4 would be down here. There's no point of intersection. So in this case, there is no solution. So you can either use your algebraic knowledge or your graphical knowledge, but either way, there's no solution. Okay, log x equals log 10x can be evaluated in your calculator. So the log button assumes that the base is 10. So if you see something written with no base here, that assumes that the base is 10. So your calculator assumes base 10, okay, and no base written means the base is 10 as well. Okay, so if nothing is written, we assume base 10. So for example, log of 500 is the same thing as saying log base 10 of 500. So you can get a calculator and actually solve this, okay? So you can find your log button. Mine's right here, log 500. 2.69897. So this is equal to 2.69897. Okay, so what does that mean? That means that 10 to the power 2.69897 is equal to approximately 500 because I rounded, so I'm saying approximately. All right, so that's pretty exciting. That's what your calculator is used for. Okay, just a few more properties I will explain before we finish this note. If you have anything, any base where the log is 1, where this is 1, then the answer will be 0. That's because any base to the power 0 is equal to 1. So if there's a 1 here, no matter what the base is, the solution will be 0. Because again, since any base to the power 0 is equal to 1. Okay, so what if you have this? Base A of a to the x. So a to the what equals a to the x. So this should be x. Since a to the x equals a to the x. Okay? Now, this one's a bit more confusing. Okay? A to the power log ax. Okay? What does that possibly mean? So to understand this, I'm going to rewrite. Okay? So I don't really get this. This doesn't make sense to me because there's all these different numbers. So I'm going to use 2 and 5. Or sorry. Let's say a is equal to 2 and x is equal to 5. What does this mean? Well, log base 2 of 5. What does that mean? Well, 2 to the power what equals 5. So I don't like that example because there's nothing that's obvious there. Okay, so I'm going to use 8 here instead, okay? Because I'm going to try to figure this out on my own. So 2 to the power 3 equals 8. Oh, that works. I can do that in my head. So that equals 3. So if I have a to the power log base 2 of 8, that's the same thing as saying 2 to the power 3. So that's 8. Oh, so this is the same thing as this. So I'm going to say this is equal to x. That's interesting. I wonder if that works all the time. Try a few more and see if that does always work. But that is the correct answer. So, sorry about this weird little video, but I hope you enjoyed it. So, thanks for watching, guys, and I hope you learned lots.